Let me just get sorted. So the next thing I want to show is batch system concept. So thanks Zaha for introducing the cluster. So what I have drawn here is actually a mini cluster, and this is animated, but that I can explain it to you, I just sort of go here, which is a PowerPoint from which I have generated that animated GIF. So what I've drawn here is a mini cluster. It has 4 nodes, each has 8 cores. So this is very suitable to explain the principles of what's going to happen. De facto, a real cluster, so the clusters we have in SNCC, they have in NAISS, they have 200 nodes, they have 1,000 nodes, and these days the nodes have way more cores than 8. So here we have the first node. It has core 0 to 7. It always counts like that in computing. We have node number 2 from 0 to 7, node number 3 from 0 to 7, and node number 4 from 0 to 7. So we have here the first user coming in, and he submitted the job number 1, which asks for 1 core and 8 hours. So then the system just takes that job and might place it here. So the time goes from left to right. So time-wise, we are currently here. So the job starts, and it is supposed to run for 8 more hours. It takes the first core, which is core number 0 on node number 1. It has to start somewhere. The next user comes in. He has a wide job, or a wider job. He wants 1 node and 8 cores for 4 hours. Time-wise, we are about here. So the system picks, okay, node number 3 looks good to me. So node number 3, all the cores are given to that user of the job number 2, and the job starts running on these 8 cores, and it's expected to continue for 4 more hours. The next user comes in, he wants 2 nodes, which is a total of 16 cores for 8 hours. Time-wise, we are about here. And the system has figured if I give node number 2 and node number 4 to that users, I can just start the job right away, and it is about to continue for 8 more hours. So this way the cluster starts filling up. Then job number 4 comes. It asks for 3 nodes, total of 24 cores, and it's just 3 hours. So time-wise, we are about here. And if you just look what's idle, it's just 7 cores. We cannot run that job because we don't have the resources available. What the system does, it has a look and it decides, okay, when I start the job here at that time in the future, time-wise we are currently here, but sort of once this job 3, which is something like 7.5, job 3, it is something like 7.5 hours to calculate still. If that is finished, I can get these 3 nodes and give it to job number 4. So this job is in a waiting queue and expected to start in 7.5 hours from now, and we can run that across these nodes. We could have also picked, for instance, these 3, but at some point the system has to decide something. It can't agonize forever. So, but anyway, if you just have a look, this job needs to wait for job number 3. So that is why that job is delayed. Then there comes the job number 5, asking for 1 node with 8 cores and for 12 hours. The problem is the same time-wise we are about here, there are 7 cores idle, and the job can't start because it wants 8 cores and we don't have that. But the system goes in and discovers, okay, once job 1 is finished, I can start the job thereafter and then run it for 8 more hours. So what you see is that here are some idle cores. It's not perfect filling. There are some idle cores. Here there are 7 cores, and here in the future, once job number 2 finishes, there's still some computing capacity, but at least at this time, there's nothing in the system which can fill that computing capacity. So another job comes in. So this is now quite interesting. So this job has a high priority. It should run as soon as possible. I will make a few remarks on priority later, but this this should has a higher priority than, for instance, job number 4 and job number 5. It wants 2 nodes, 16 cores of 4 hours. Time-wise, we are about here. The job can't be run right away. That is one of the policies in NAISS. A job which starts running doesn't get terminated. So the job needs to be pushed on the waiting queue, but it should get the top spot on the waiting queue. So if I just go back to show that more clearly what happened, so here we were there. So what the system has done, it has moved job 4 and job number 5 back in time. So here originally job number 5 was about to start here. If I move forward, you see it got delayed by that much. And job 4 got quite delayed. Then once this job number 1 has finished, here is some gap, job number 6 can start. And job number 6 will start before job number 5 and job number 4. That is the earliest the system can do, and that is where it gets placed. Another job comes in. It asks for 1 core at 6 hours. Time-wise, we are about here. So here there are 7 cores idle. But this crucial thing is this one here. The job asks for 6 hours. And from here to there until job number 6 starts, there's not 6 hours left. And this is not a job of high priority. It can only be done after job number 4 has finished. So here, this is something which we often get from new users, which are not experienced, that look, I look in the system, here a bunch of cores idle, why can't you not run my 1 core job? And the answer is because you asked for 6 hours, and currently we cannot assure that your job gets you 6 hours before we run something quite important. So one thing to take back from that already is that if you want your jobs to start soon, don't give ridiculous large job times. So a lot of our systems offer for 7 days of running, and we have a large number of users which just can't be asked to estimate a proper job time. They just write 7 days on everything, and then they wonder why the job gets at the end. If you have a short job of 2 hours, which then it might start a lot sooner than if you write 7 days. Still, we will discuss that later. Don't get too aggressive. If you just tell us 2 hours, the job gets stopped after 2 hours, irrespective of whether it's finished or not. So in general, you have to overestimate. So that is here the thing which I just discussed. A job number 8 comes in. It asks for 4 cores, but quite a short time, 2 hours. And here there's a perfect lot. There's a perfect lot. That job is quite short. It runs directly on node number 1. So here's a few things for you to take away. So jobs overtake each other. So just the systems are typically not what comes in first runs first. So for instance, job 8 just came in, but the system found a hole where it can put it in, and it can run it directly because it asks a modest size of cores. If it would have asked for 32 cores, it couldn't be run here. It had to go to the end. But it asked a modest size of cores. It asked 4 cores, asked a short time, and then the system discovered a gap in the scheduling where it could run the job right away. Job times, as I said, this 2 hours. So I think if I have a job which I expect to run 1.5 hours, specifying 2 hours is reasonable because these things don't reproduce always exactly. So if you just have a look, job number 8 is placed on a node together with job number 1, and the computational speed of job number 8 might depend on what job number 1 does. Is job number 1 writing a lot of output? Is job number 1 getting a lot of memory data from main memory back to main memory, or is it just memory friendly? That will affect job number 8. In turn, job number 8 will also affect the performance of job number one. So jobs are not perfectly. So if you perfectly reproducing, this is just the nature of a shared cluster resource. So I would think that 2 hours, if you specify 2 hours, that's reasonable for a job which is expected to run 1.5 hours, 1.7 hours, something like that. So don't get, so this number, what you specify, always have to be slightly larger than what you expect, but don't get ridiculous. As I said, if that job would have specified 7 days, it could just go to the end. So that is this animation. Let me go back to my to the text. So here you have the animation, and here you have the full description of what I just said, the rationale. So key points. What you have to do is to submit the jobs to the waiting queue. You do that on the front end. Jobs start executing once it is their turn. That might be right away if the scheduler finds a gap, or it might be some at a later time. The system is running 24/7 unless there are problems. And so it might be that the start time of your job is tomorrow morning at 3 o'clock. That is normally something which you don't sit in front of the terminal. So you have to describe the computational work right now when you submit the job. Once it is my turn, what should the system do? And that is typically done by a script. So you write a small Unix script, where we had some of that yesterday already, and there will be more in the Linux 201 on writing scripts and on general scripting. And in this course, we will discuss with you how a simple Slurm script based on what we taught yesterday looks, that you can detail to the system what it should do once it is your turn. The next point, which I just skipped or jumped, is that the anticipated start time can move backwards or forward depending on other users' action. So as I said, it's good practice to slightly overestimate the time you're using. The scheduling is based on the time the users specify in the script. So most jobs will finish early. And then based on that, the scheduler might suddenly rejig a lot of things because some job has finished, and things get reordered. So you can query the system. We will teach that later. When does your job expected to start? But for the reasons which I showed in the animation and I just outlined to you, it might be that it typically is that the job time will change once as long as you wait. A few things on priorities. The priorities of the jobs are affected by a number of factors. These may include the time the job has already spent in the queue, how many resources, for example, CPU hours, the project has already used in the allocation to the resources. So many, if you have been granted, let's say, 20,000 core hours on a service for a month, if you have used in the last 30 days already 25,000 hours, you typically get a lower priority, that those which have not overdrawn their account can run first. But at some point, most of the systems will still allow you to run. The rationale is if the users which still have not spent their allocation do not submit jobs, then we prefer to run jobs from people which have already spent their allocation instead of having the system idling. So a project which has overrun the allocation typically gets a low priority. A project which hasn't spent so much of the allocation typically gets a high priority, that they can spend the allocation. And these rules are often not static. System administrators quite often look into the system and change the rules if they notice that some users get too little or too much resources compared to their allocated project, such that the system is fair. Okay, that is what I